Good morning, everybody. Okay, so homework number 9 is available now on Blackboard. It's due Tuesday of next week. And homework 11 will be due on Monday of the following week. Now, that's an unusual thing that we'd have a homework assignment due on Monday, but the reason for that is I wanted to give you as much time as possible, but also have the solutions up for at least some time before you have the exam the following day. So it will be due at noon automatically. The solution will be visible right at 12 o'clock on Monday, and then we have our exam in class on Tuesday the 19th. And so that's the Tuesday, the last Tuesday that we'll have before the Thanksgiving break. Any questions on the announcements? We're going to begin talking about Chapter 6 today in the book, Momentum. And it's the third of the 3 chapters that are included in the material for the second exam. And in a future class, I'll give you some more information about the format of the exam too, but it's largely going to be the same as how things worked with the first exam. Okay, now before we start talking about momentum, I wanted to revisit what we did in lab this week and see if there are any questions that you have related to the design of experiment activity, where you remember that the lab is going to be open each day until Friday of next week, and your objective is to go in, become familiar with the equipment so that you can write a procedure, think through the introductory material that needs to be provided to someone who didn't get the same first-hand exposure to the equipment as you. So, usually when you get the handout from me before the labs, that'll have a pretty bare bones and basic procedure, and the reason why it doesn't have to be quite as lengthy is that then I give a demonstration on how the equipment is operated, some safety things to look out for. You actually have somebody there in front of you demonstrating the equipment. But for the handout that you're going to be generating, you need to write the handout for someone who isn't in the class and hasn't used the equipment previously. And so they're going to need to know everything from how do you quantify flow rate, instructions on how to calculate the velocity through the pipe. So think about all the formulas that are going to need to be included in that lab handout for people to be able to calculate the things that are going into this equation. So in the handout, you're telling some hypothetical fluid mechanics novice, but who finds himself in the lab needing to classify the Hayes-Williams roughness factor, the procedure, the data table, all the same elements that would go into a lab handout. So part 1, when you actually execute the experiment, part 1 of what you're going to be doing is find experimentally what is the average C sub H value. There's going to be a slight variation in C sub H value for the small pipes versus the big pipes. In theory, it should be the same regardless of diameter, but it won't be. In theory, it should be consistent over a range of velocities, but again, it's going to vary slightly, and so you find out what's the C value on all these different conditions, and then you're going to calculate an average C value. Once you've determined that average C value, then what I'd like you to do when you're conducting the experiment and analyzing the results is test the Hayes-Williams equation and see if you've got some average C value, how well does the Hayes-Williams equation predict the pressure change. And so you're going to use the pressure change to calculate the C value, and once you've got the average C value, take that C value and predict what the pressure change should have been and compare it to what was experimentally observed. And so then you'll be able to do like a scatter plot of measured versus experimental, that 1-to-1 graph that we've done in a lot of our labs just to illustrate whether the data is consistently too high, too low. You'll be able to calculate an average percent error on how well the Hayes-Williams is predicting the pressure change, and so on. So the 2-phase project The lab handout part of it maybe is even more important than when you put together the report, at least from a points perspective, because the points for the handout is 20% of your overall lab grade. So let me know if you have any questions as you're working on this, or if there's any issues with the equipment. It's an important one, so I want it to be really clear what the expectations are. Remember, the lab handout needs to be submitted by Wednesday of next week. Is that right? Wednesday of next week. And then the report will be due before lab the week before next, because we're not going to have any lab meeting next week. All right. Any questions about the lab? Yeah.
So the change in pressure will be determined during the lab, but
yep.
Will determine a theoretical value as well?
Yeah, you'll measure the pressure in the lab, and that's how you're going to determine the C sub H value. Because if you look at the Hazen-Williams equation, the only unknown will be C sub H, because you'll measure the velocity indirectly. You know, you'll have the flow rate and the diameter, and that gives you the velocity. You know the hydraulic radius, the S sub F you'll get from the measured pressure change, and so C sub H will be the only unknown, and you'll come up with an average C sub H under the range of conditions and across all the pipe diameters, and then you use that to come up with predicted pressure values and compare it to what was measured. Okay, well, I guess we should watch some YouTube videos today, so let's get started with that. Here we go. Okay, let's review the terms of service. Jeez Louise. Let me get the audio going though. I'm not sure why we don't have any sound. No.
It's on the YouTube, the video itself. And it's the...
Still no sound. Let me just try one more thing here. I guess the sound's not the important thing. Alright, we'll have to do this one without sound. Let me start from the beginning. I'll narrate. This is my brother. This is when he and I went to Dubai in June, and we went to a place where they strap you into these boots and then connected to like a wave runner by a long flexible pipe are these jet boots. My brother got up right away. This is after I fell over continuously for like 20 minutes, and he stood up on his first try like a natural. So, but he's fat though, so that's a joke, right? Obviously. So the reason I mention it is it's going to come up in the calculations we do. Yeah. He's better looking. I make more. So anyways, yeah, brotherly competition. So he got right up on the boots, and he even does a little dance here in a minute. The guy was worried. Yeah, you're being too crazy. But yeah, so let me pause. This is a good view. So you can see that we are on a wave runner, and the wave runner is just drifting around. But out the back, the way a wave runner is propelled, it doesn't have a propeller. It's got a pump inside of the wave runner. And so it's a big pump with a gas engine connected to it, and it sucks water in the front and it pumps water out the back. And so there's this flexible hose that's connected to the discharge pipe on the wave runner. And so this flexible tube is just kind of like under the water, and then you can see it going up. And so this is a really simple setup. There's water flowing up through the pipe. It gets split and then redirected downward, and the water is going out through these jets. And the jets can pivot independently. And so the way that you move around is you just kind of lean forward, and when you lean forward, the center of gravity is ahead of the jets, and that kind of tilts the jets backwards, and it starts moving you forward. So, watch it seems taller than it is. When you're on the boots, I eventually did. When you're on the boots, it feels like you're the king of the world at the top of the skyscraper. It's really probably only 11 or 12 feet. See the Burj Khalifa in the background? It's a big one.
He wants to go down.
All right.
Down, down, down.
So why do I show you this video other than to rag on my brother? It is because it's the perfect application of the momentum principle. What we're going to be talking about over the next couple of lectures are some specific applications of fluid momentum. So let me, as an illustration, show you some calculations related to what we just saw. My brother weighs 245 pounds. At least he did then. I don't know what he weighs now. Probably more. No. I guess I'll lay off. So what we need to know is what is his mass in kilograms, and then what's his weight in newtons, right? So eventually we're going to do W is M times G, but for 245 pounds, do you know the conversion between pounds and kilograms?
2.245 pounds per kilogram.
2.2, I thought it was 2.21. I mean, I'm not exactly sure. Let's see. Because I do have units conversion in my calculator. So, 1 kilogram to pounds, 2.204. Did you say 04?
Yeah,
Okay.
zero.
So, 2.2046 pounds per kilo. Okay. So will you tell me what is that mass in kilograms?
111.13.
111.13 kilograms. And then the mass is 9.81, excuse me, G. 9.81 meters per second squared. And so my brother is 1090 newtons. 1090 newtons. Okay. The flow rate through that, the nozzles, is variable. And the way it's controlled, it should be more precise than this, but it's just the guy on the wave runner with his thumb is controlling in the same way that that you use a thumb throttle to move the thing through the water. He's kind of just watching how high he thinks my brother should be at any given time. And if he thinks he wants my brother to be higher in the air, he'd turn up the throttle, and that would increase the flow rate through those boots. But I think a typical flow rate, having also had them strapped to my feet and seeing how quick it's going out, let's just say that each of the nozzles has 10 liters per second of water going through there. Okay, so if the Q is 10 liters per second, and that's each nozzle, then what's the mass flow rate in terms of kilograms per second for the combined mass flow rate through both jets? Come on. M dot is density times Q. So what's how many kilograms per second of water is going through the jet boots? Water is 1,000 kilograms per cubic meter, or 1 kilogram per liter. A liter of water has a mass of a kilogram. So if each of the two jets is 10 liters per second, then the mass flow rate is how many kilograms per second?
1,000.
It's
10, right.
10 liters is 10 kilograms, and there's two of those. So in total, we have 20 kilograms per second that's going out through the boots. All right, so if we want to know what's the jet velocity, what we can do is use the equation that the force is the mass flow rate times the velocity. And when he's in equilibrium, the force that's holding my brother up is equal to the weight. And so we can rearrange that to solve for velocity. It's going to be the force that we know divided by the mass flow rate. And so we're going to check and see if these units work out. But the force is 1090 newtons. And by the way, remember, a newton is a kilogram meter per second squared. So 1090 newtons divided by the mass flow rate of 20 kilograms per second. Okay, so we have 1090 divided by 20, that's 54.5. And what's the units that are left once we cancel things out? Cancel out the kilograms, cancel out we put the seconds here into the numerator there, then it'll cancel out one of the seconds in this one, so it's meters per second. So the velocity of water out of those boots is 54.5 meters per second. Now the reality is that with the thumb trigger, when the person is increasing the flow rate, they're simultaneously increasing the mass flow rate and also the velocity. So both of those things are going to be going up as the pump inside the wave runner increases. But it's a kind of an interesting application of the momentum equation. Let's look at another one. That was where the fluid was water. Similar thing, someone strapping a jet to their feet. This time it's going to be a jet of air rather than a jet of water. Oh, this one we really need the audio. I'm so bummed out. Maybe it's the browser. I mean, you know, who uses Edge? Let me see if we have any better luck with this one.
Ei ihan kevyt olekaan. 3 kiloa kappale painaa kenkä. Siinä on kaikki polttoainekuluja valmissa.
Oletko kokeillut lenkillä? Lisääkö juoksutehoa?
Ei no.
Tuolta sitten niinku
Oh, the TV itself may be muted. Yeah, maybe. Good point. No, it's way up. Oh well. I'll have to narrate this one too. All right. So let me narrate this. This guy's in Finland, and he's a wingsuiter. You know, the guys who normally would jump off a mountain or jump out of a helicopter and they'll just coast. But he's taken some He's taken some hobby.
Eihän paljon
tohka.
These are kind of jet engines
3
that
kiloa kappale
normally would be
painaa.
connected to
On kaikki
like
polttoaine tulee vallassa.
Oot sä kokeillut lenkillä? Lisääkö juoksuteho?
connected them to boots.
Niin no.
Tuolta sit niinku hönkää.
Lisa,
No.
And
What are you gonna do with
during
us?
the winter,
Fly. I like
there.
flying.
So here in a moment, they're gonna prime the boots with like propane to get it heated up, and so that's jet fuel that he's carrying around. He's going to stuff into his wingsuit. So it's not enough that he's skydiving, wearing a wingsuit, but he's got a bladder full of jet fuel. So he's just revving up the engine, getting everything tested and warmed up. By the way, sorry that the video quality isn't better. This was posted like back in 2005, and then the guy suddenly stopped uploading videos.
This is Finland, very rough country.
So I've assumed the worst. I haven't been able
But
to
just say
find any updates.
that this kind of weather, if you land
So
on
he's
the
up in a
water, you're
balloon
gonna
right
die.
now. Jump out there. The objective is to maintain level flight. Because normally a wingsuit falls down survives this one. Lower at this point, so he's definitely, he narrates at the end that he achieved level flight for a little while and then he tried to climb, but then he stalled. You know, the wingsuit stalled. He has a parachute on. You don't see that, but obviously.
Hey, I was fucking first one to do it. I jumped from 2,200 meters and flight until
All right, so here's the specifications. He's got 16 kilograms of thrust on each boot, and it was primed with a mixture of butane and propane, but then that was like a refined kerosene. It was jet fuel that was going through there, and it's burning at a rate of 0.5 liters per minute for each jet. So he's not able to carry a lot of fuel, and that's one of the things that limits. And he was at 7,000 feet when he first jumped out, and then attained horizontal flight, but then it stalled when he was trying to gain some altitude. What we're going to do is we may come back to this and do some calculations related to the mass flow rate and the velocity. So we'll see if we have the time to come back to that. I want to show you where that equation that I used earlier comes from, how it's derived. So everybody's familiar with Newton's second law, that the sum of the forces that are applied to an object account for its acceleration. And so if there's an imbalance of forces that are applied, if an object is being pushed on one side more than the other, if there's an imbalance of forces, then you could calculate its acceleration by dividing by mass from that force. So Newton's second law, and if we substitute, what we mean by acceleration here is the change in velocity over time. So we're talking about local acceleration for Newton's second law. And instead of a particle of mass, what we're going to do is eventually we're going to apply it to a stream of mass. And so what we'll do is we'll combine the mass and the velocity together, and call that the momentum of the system. So mass times velocity is momentum. And the system is a continuously connected number of particles that can be, in our case, a liquid or a gas, but it's a fluid particles that can change their location in time. And if we apply the Reynolds transport theorem, remember that the change of momentum of a system over time can be accounted for by keeping track of what's flowing through the control surfaces and the accumulation that occurs inside of the control volume. Now, the accumulation of mass is pretty uncommon. It's becoming used a little bit more frequently in like electric cars, where there are flywheels that will spin and preserve some of the energy as a vehicle is braking. But most of the time what we'll do is we'll neglect the accumulation of momentum and instead just focus on the flow of momentum through the control surfaces. And so let's look at this transport term a little bit more closely and what we've got included there. So the transport term, remember that if we have a velocity of a fluid multiplied by the mass flow rate, and mass flow rate m dot, here I said it's density times the volumetric flow rate, and we could expand that further to be density times the velocity times the cross-sectional area. And so that's what we have here. Density, velocity, cross-sectional area, and then the other velocity that you're multiplying by the mass flow rate. So the flow through the control surfaces is going to be pretty important when we're doing momentum problems. We're going to have to draw the control surfaces that encompass a control volume so that we can define where it is we are using as our reference point for streams of mass flowing in and flowing out. So now if we combine the Newton's second law and the Reynolds transport theorem together, then on the left-hand side of this, instead of saying the change of momentum in the system over time, instead we're just saying it's the sum of the forces. And so when jets move, there's an imbalance of forces that are caused by the deflection of a jet, and that's how you're able to have things like the jet boots, where it's producing a velocity through combustion, and the fast-moving velocity of that jet combined with the mass flow rate, the combination of the fuel and the air together is what gives you a mass flow that's out of the control volume. Usually there will be no momentum accumulation, and so we can simplify and cancel out that term.
Energy storage
Here
flywheel.
is an exception to that. I don't know why it suddenly would start working, but I guess I can always hope.
Have
This is
very
showing
high performance and work on simple principles.
Sure,
To
let's do
understand-
that. Good idea. Thank you.
Energy storage flywheels have very high performance and work on simple principles. To understand their operation, it is best to start with the electric motor generator. An electric motor and generator are really the same machine running in opposite directions. When you put electrical energy into a motor generator, it turns into mechanical energy
awkward,
on the
right?
spinning shaft. That's a
We're
motor.
sitting here in silence.
When you put mechanical energy into the motor generator by spinning the shaft, you can draw electrical energy
So
back
we're generating
out.
electricity
That's a
when you
generator.
apply
For an energy
mechanical
storage
work
flywheel,
to
we hook a motor
the
generator up to a wheel.
You can spin the
When we
flywheel.
put electrical energy into the motor
It's
generator,
taking-
it
it's
accelerates
taking
the
energy
wheel,
to get it
storing
moving,
that
but
energy
then
as
when you
momentum
stop adding
on
the
the wheel.
electricity,
When we want our electricity back,
the motor
we let the
then it
momentum
turns
of the
into a
spinning
generator
wheel drive
as
the motor
it's
generator,
slowing down. You could
regenerating
extract
our
the
electricity
electrical energy.
and slowing the
So
wheel.
this
Because
is
we run our flywheel
an
in a
illustration
vacuum
of
and on
how
very good
momentum
bearings,
can
we don't lose much
accumulate
energy over time.
during a period of time,
Velkus
and
has
then it can
invented
be
a new
that
way to
accumulation
make
can be
energy storage
extracted as
flywheels
well.
at very low cost.
But for most of the problems you'll see in the homework, we will cancel out the momentum accumulation, and that's because the parts will be stationary and we'll have steady flow conditions. And what the momentum equation will simplify to then is that the sum of the forces is equal to the flow of the momentum through the control surfaces. There may be multiple streams that we have to keep track of, and that's what kind of makes it tricky, is that there's a convention for the direction of the jet, and there's also a convention that we'll have to ask ourselves if the stream is going in or out of the control volume. Now, by the forces that are acting, what we're talking about is surface forces. So there's physical contact between the jet and a deflection vane, as an illustration. And it's not body forces, it's not gravitational or electrostatic or magnetic forces that arise when there is a change in momentum, but it is surface force. So this is the form of the equation that we're going to be using for problem solving, in the same way that you kind of had to take this theoretical equation for the Euler's equation and then apply it to a direction. You know, this is independent of direction. But if we wanted to apply the momentum equation for forces that occur in the x direction, then this is how we would do that. And what it says is that the mass flow rate out of a control surface multiplied by the velocity out in the x direction. So you'll notice that we're only keeping track of what component of the jet's velocity is in the x direction, and then minus those same things, but now this is for the flow in to a control volume rather than the flow out. So if you accidentally switch the two, then you'll get a wrong answer in terms of whether the force is positive, meaning to the right, or negative, meaning to the left. And then also this velocity term is a vector where you have to have in both the magnitude of the velocity but also its direction. And so if the velocity of the jet is in the opposite direction of to the right being positive, so if the jet velocity is to the left, then we would have to put its velocity in a negative terms when we're substituting into the formula. Of course, it can also be expressed in the y direction. One thing I'll point out with these subscripts is that the mass flow rate, it's the entirety of the mass flow rate. And the mass flow rate is just a scalar. It's not a vector. It doesn't have direction. And so we don't have to consider like negative mass flow rates. That doesn't exist. There are only positive mass flow rates. But then it's the entirety of the mass flow rate out versus in. Mass flow rates also don't have direction, so we're not trying to find out like a component of the mass flow rate in the x direction. So sign convention is important, and we'll have the same sign conventions that we used when we were doing Euler's equation, where to the right is positive and up is positive. Now, here's a sample control surface, and we have a stream that's going in, a stream that's going out, and so let's just, for practice, think about the velocities and how they'd be substituted into this equation if we had a stream of water coming in to the right and a stream of water going out to the right. Then both of those, the velocity out in x is positive, velocity in x is positive. Okay, so now what about this one, where we have stream 1? You can see that the velocity out, okay, in the y direction, since it's down, it's negative. Velocity in at 1 is to the right, so it's positive. Velocity in at 2 is to the left, so it's negative. Okay, what about for this one? What I'd like you to do is, in your notes there, do the same thing that we did in these previous two examples. Okay, stream number 1. Is it an in versus an out? And is it positive or is it negative? And we'll go through it together in just a moment. Okay, so velocity in 1 in the x direction is to the right, so it's positive. Velocity in of stream 1 in the y direction is down, so it's going to be negative. So whatever that velocity of the jet is, when we substitute it into formula, we would need to put a negative value here in the in term. All right, so stream 2, all right, velocity, stream 2 is an in, so velocity in through stream 2 in the x direction. Is it a positive or a negative?
Negative.
Negative, right, because it's to the left. Good. And velocity in at stream 2 in the y direction. Positive or negative? Negative, good, because it's down. That's right. Finally, velocity out at location 3 in the x direction. So it's going out of the control volume. Positive or negative x?
Positive.
Positive, right, because it's in the rightward direction, and the velocity out at location 3 in the y direction, it's going up, and so it's positive as well. All right, so just pay special attention to whether a stream is in or out compared to the control volume, and then whether it will be negative or positive when you substitute the velocity into the momentum equation. The momentum equation is sometimes a little bit tricky because you won't necessarily be given where is the control volume in the sketch or in the problem statement. Sometimes you have to decide where you should put the control volume. And the way that you know how to do that is you just draw the control surfaces so that it encloses the system of interest. You know, if you have, for example, a jet of water that's coming in contact with a plate, and it's deflecting the water as it does that. So I think you have a problem like this on the homework, where there's a jet of water, it impacts a metal plate, and through the impact that causes the spray, part of the spray to go up, part of the spray to go down. So to know where to draw the control surfaces for this is you need to draw the boundary around where the change occurs. And so what we do is we just draw our boundary like this. And I think in the problem what it's asking is what is the force required to hold the system steady? So the jet, as it's changing direction, is pushing on the plate to the right, and the plate is pushing on the jet to the left, and then the system is in equilibrium if those two forces are equal. So as far as sketching the system, you'd need to put the control surfaces around where some change occurs, like where there's an interaction between the jet and some deflector. There will sometimes be combinations of equations where we'll have a problem with momentum that also has a Bernoulli's application. And so one illustration of that comes to mind would be if we had a system that was a nozzle and there's a jet of water coming out and we're pushing on a plate here with some force to pressurize. Like think of it as like a plunger of some sort. You know how like you press on a syringe to squirt the water out of the syringe. What if we were doing a similar thing where we had a plug, we're pressing on the plug to force the water out of the nozzle? So this could be a combination problem where we're looking at the mass flow rate and the velocity of this, and we want to see, when it blasts into this, then what force is required to hold it steady? Well, you can combine that momentum aspect of the problem with a Bernoulli's aspect where we need to know, in order to calculate the velocity of this jet, we could find out the Bernoulli's equation, remember, the pressure at 1 plus the gamma C1 plus V1 squared divided by 2G is equal to P2 divided by gamma plus Z2 plus E2 squared divided by 2G. So we could use the Bernoulli's equation between location 1 and location 2 in order to find out what's the jet velocity if we were pushing on this with some certain force. So that's an example of a problem type where there may be multiple governing equations that apply in the same problem beyond just the momentum equation itself. The suggestion is also in the book that you try and sketch also any external forces that are applied and pay special attention to the direction of the force that's being applied. And if the force is to the left, to the right, and what that, how that applies to our assumed directions for the convention. And then sketch the momentum flow vectors, just sketching the stream of water, the stream of air, you know, the momentum flow being the system itself as it moves. Okay, so let's get a chance to do some additional calculations here. Let's say that we have a balloon and there's air inside of the balloon that's exiting through a nozzle, and the balloon is connected to like a straw on a string. So that holds it steady rather than just flying around randomly. It's going in a straight line, and we're interested to know what's the exit velocity of the gas as it goes out through the balloon, and then also what is the force that would be required to hold that balloon steady so that it doesn't accelerate to the right. In the problem statement here, it's mentioning what is the pressure inside the balloon, and it's mentioning that in terms of meters of water. It says that the pressure is 0.4 meters of water. So normally we measure pressure in pascals or newtons per meter squared, but there are, it's fairly common for pressures to be described in terms of a height instead. And so the way that you would get the pressure when it tells you some distance is it means the equivalent pressure at a depth of 0.4 meters. So you just use the hydrostatic equation. You would say delta P is delta H times gamma. So when they say the pressure is 0.4 meters of water, they're just saying 0.4 and 9810 is the pressure. Okay, so with what you've seen so far, I'd like you to calculate the exit velocity, and you can do that with Bernoulli's equation inside the balloon. Inside the balloon, what that looks like as far as Bernoulli's equation is a balloon where you've got some gas that's coming out, and location 1 is in the center of the balloon, and the balloon is kind of shrinking inward, and so we're going to assume that right in the middle of the balloon that the gas is not moving at all. The gas is going out in the vicinity of the nozzle, but right here at the center of the balloon the velocity is stationary. We know the pressure there. We can see by inspection that the elevation between location 1 and location 2 is the same. So see if you can use Bernoulli's equation to find the exit velocity of the gas, and then once you have that, draw a control volume to find out what's the mass flow rate in, none. What's the mass flow rate out, velocity out, and find what force we have to apply to hold the system steady.
On the 0.4 meters, is that the change in height?
Yeah.
Okay. Never had a pressure in meters before.
Okay, so they've given us the pressure in the balloon in some weird way, these depth of water units. And so the first thing that we do in the calculations is convert those depth of water units into the pressure that we can actually substitute into Bernoulli equation. So that turns out to be 3924 newtons per meter squared. I also did these incidental calculations at the beginning here for the cross-sectional area of that nozzle that the air is flowing through. And so if it's 1 centimeter, then that's 0.01 meters, and we get the cross-sectional area of the orifice that the air is coming out of. Okay, now Bernoulli's equation, we cancel out several of the terms because if location 1's at the center of the balloon and location 2 is here in the jet of air is not pressurized. Once the air comes out of the nozzle, then it takes on the same pressure as the surrounding atmosphere. So that's why we can cancel out P2. We can cancel out both Z1 and Z2 terms because this is horizontally oriented. They're on the same elevation plane. And there's no velocity at location 1. It's at the center of the balloon, and the balloon is collapsing with the center of its inward collapsing being at 1. Even if it wasn't, the velocity would be so small compared to the discharge velocity in this orifice that it could be neglected. So we rearrange Bernoulli's equation and calculate that the exit velocity 80.87 meters per second. And that velocity is to the left. It's really important when we start putting things into the momentum equation to keep track of the directionality of a flow. All right, so the momentum equation we've got in the x direction, we're keeping track of the mass flow rate out, velocity out in x, and then minus mass flow rate in, velocity in x. There's no flows in, it's just a flow out. So the equation then, and there's only a single force applied, so the equation simplifies to this. Now, a word of caution. Sometimes, since velocity is in both the mass flow term and we're multiplying it again by velocity, it can be tempting to say that your equation is going to be f of x is the density, area, velocity squared. Because it's density, area, velocity, that's your momentum term, and then you're multiplying it by velocity again. If you do this, though, you run the risk of not knowing when the force is negative versus positive, because when you square a number, if the number was negative, then now it becomes positive. Now, keep in mind that mass flow rate is a scalar. It doesn't have direction, so it's only going to be positive. So we're going to have some mass flow, and I've calculated that separately here. The mass flow rate is 7.62 times 10 to the minus third kilograms per second. Now, there couldn't be a negative mass flow. It's just the mass flow is that, but then the velocity is to the left, which means that when I do the substitution here, I need to make sure to put that negative sign into the velocity. So that if I had used this expression and I put in minus 80.87, then the force would be positive. But when I do the calculations, the force should be negative, indicating that the force applied is in the left direction. And you can usually, for a problem as simple as this, where you can kind of see it and picture and you have an instinct for what's going on, you know that you're going to have to push to the left because the balloon wants to move to the right. But there are going to be some problems that are a little bit less obvious, like in the case of a nozzle where there's a jet of water that's going out of a nozzle. If you apply the momentum equation through a control volume like this, it's not immediately clear if you had a flange like this, whether you have to push to the right or to the left as a result of that nozzle. We'll talk about the fact that you have to consider the pressure in the pipe as an external force applied at the control surface boundary, but for now just keep in mind that the direction of this velocity is really important to get the correct magnitude, to get the correct direction in the force that's applied. And so always be explicit about what direction you mean. So here I was showing that the force is to the left. Here the negative sign indicates that it's to the left, and what I should have done is I should have, in the note down here, I should have said the external force to hold the system steady is to the left. I should have made it, I should have a third time clarified the direction that I intended my answer to reflect. Any questions on the calculations here? All right. I think we have one more YouTube video to watch here. Flyboard Air. This is before the guy got across the English Channel. He was just doing flights around the...
and perfecting. That's the mark of a maker.
When this video was...
When the first video of this invention appeared on the internet, some people just couldn't believe it was real. But it is. It's the Flyboard Air from French jet ski champion Frank Zapata and Zapata Racing. Having previously developed a hugely popular original Flyboard, a similar-looking water-powered craft, Zapata Racing has taken a major step forward with the Flyboard Air prototype. Usher in a Omni hoverboard. 5 years in the making by Canadian Alexander Duru, the Omni started out with not much more than a propeller and motor strapped to a piece of wood. Finally, a similar-looking water-powered altitudes of up to 10,000 feet with a top speed.
All right, so he's got a backpack full of fuel. He can carry more than the guy who had it stuffed in the wingsuit. But it's a series of ducted fans inside of here. And so let's do some calculations related to that. If in the Flyboard, the rider is 80 kilograms, the board and fuel is 20 kilograms, and so there's a total 100 kilograms of mass that's being supported by the momentum. And if you're burning 2 kilograms of fuel per minute, and then the fuel to air ratio is what's going to tell you the mass flow rate that's actually coming out of the boot, that's coming out of the control surfaces. And so it is here we've got some mass that's being supported by the jet that's coming out, and the mass flow rate is going to be, if there's 1 kilogram of fuel that consumes 3.5 kilograms of air, then the exhaust that's coming out has a mass of 4.5 kilograms. That's the total mass of what's coming out, because the combustion reaction is fuel plus air, and so for every 1 kilogram of fuel that's being used, then you're also discharging 3.5 kilograms of air coming out of that. So what I'd like you to do here is, we know the force that has to be supported because the mass is known. You can calculate the F sub y. We don't have any flow in. There's just a flow out through the control surfaces. And so calculate what velocity has to be achieved out of the jet, with this assumed fuel burn rate to support the rider and the board plus fuel to generate enough force for level flight. Is there a question?
We're just assuming there's one jet.
Yeah,
Okay.
that's right. A 100 pounds is the mass of the rider plus all of the equipment, so that's 981 newtons. And if you're burning 2 kilograms per minute of fuel, and 1 kilogram of fuel gives you 4.5 kilograms of exhaust, then you can see that the mass flow rate is going to be 0.15 kilograms per second. So that's the mass flow rate of the exhaust. So the best case scenario is that when the person first takes off, then there isn't going to be any mass flow rate or velocity associated with what's coming into the engines. As the person is climbing upwards, actually they're going to lose thrust because there will be a mass flow rate and a velocity that's coming into the jets. But we'll neglect that for now and assume the best case scenario generating the most thrust. So with a mass flow rate of 0.15 kilograms per second, then the velocity in this case would need to be 6540 meters per second. Now I just assumed a mass flow rate of the exhaust. This is an extremely high velocity. It may be that they're burning more than 2 kilograms of fuel per minute. But that's your first exposure to the momentum equation. The three problem types that we'll be solving with it are fluid jets, vanes, and nozzles. So in class next time we'll look at some examples of fluid jets and vanes. I'll see you on Tuesday next week.
Now, on the lab report, on the CH value, we're